Hello guys, welcome to the sixth video of the uh, Black-Scholes European option pricing model derivation. In the previous video, we talked about the graphical representation of Brownian motion, and in the video before that, we talked about the mathematical definition of Brownian motion. So to give a little recap on everything that we've learned thus far, we know that B of t is what we call a Brownian motion. And we know that this is a continuous time stochastic process. Essentially what stochastic means is we add random elements to it. Whereas in probability and statistics, we're usually given a random variable and we're told to find characteristics of it, such as expected value, variance, standard deviation, so on and so forth. But it's important to add a stochastic element when modeling a financial asset, because in the real world, financial assets do move with a stochastic nature. So a few things that we concluded throughout the past few videos. We concluded that B of 0 is equal to 0, meaning our Brownian motion starts at 0. We also constructed our Brownian motion in such a way such that every next point is a normally distributed random sample from the previous point. We also noted that our one standard deviation, or 64% probability that our Brownian motion will end at a certain time, is a function of time. So to write that mathematically, I could say B of t follows a normal distribution with mean 0 and variance t, which I can then rewrite as a standard deviation of square root t times my normal distribution function of 0 and variance 1. And something else that we concluded is B of t is continuous on 0 to t, and B of t is given such that dB of dt does not exist on the same interval 0 to t. We also know that Brownian motion has a quadratic variation, which can be written as dB squared is equal to dt, or it can be written as dB is equal to square root dt. Cool, so let's put this into graphical representation one more time and start to relate it back to stock price and how we can add it into this model. So the most important thing is that we have a one standard deviation of square root t and negative square root t. So if I have, let's say, I'm interested in my Brownian motion at 1, then I have a 64% probability that my stock prices or my Brownian motion will land in this interval right here. Now, at 3, for example, I have the same probability that my stock prices will land within this interval. So this would be negative 1, 1. This would be square root 3 and negative square root 3. Now, in regards to stock prices, why does this make sense? Well, a simple thought experiment, if you will. If you have a stock price trading at $100 and you are interested in the stock price on the next day, well, it could either, let's say, go up to 101 or go down to 99. But if you're interested within the next minute, it's probably not likely to go past a few cents. Whereas if you're interested in the next year or so, it can rise up to 10, 20 and dollars and fall that same amount. So that's why as we go further in time, we are less certain about where our Brownian motion will end up, especially once we reach the final stopping price that we're so interested in. Another thing to note is our expected value, at least for a Brownian motion, is always going to be 0. Even though our variance increases and therefore our 64% standard deviation increases, our expected value of what our Brownian motion will be is always going to be 0. Cool. So let's talk about the standard deviation and variance of a real stock price. So let's take an example of a stock. Say it starts here, and then one stock is going to go like this with some sort of geometric drift. And let's say there's another stock with the same exact geometric drift, mu, but it moves a lot more. So we have S1, which has S1 of t, which we're going to say low volatility, and S2 of t, which we're going to say high volatility. So we have this term called volatility, which can be measurable in stock prices, right? And essentially what volatility is, if I were to give a definition, it's how prone, in this case, a financial asset is to change. So in the context of Brownian motion, if I were to just analyze the noise residual of this without really thinking about the mean returns, if I were to graph out t, and let's say this is S1 of t, I'll probably get something like this as the noise. Whereas S2 of t will probably look something more along the lines of this. So again, this is low volatility, and this is high volatility. So if I were to do a real-world example, let's say I have a stock price S0 trading at $100, and let's say I have a low volatility constant of, and I'm going to denote volatility as such, and let's say it's 0.01, and let's say this is my low volatility. Well, in my next day, my stock price can either go to 101 or it can go to 99, right? And let's think that our mean returns is going to be 0 for simplicity's sake, just to demonstrate the contribution of volatility. Now, this is for my volatility low. Now, in another case, I could have my volatility high being 0.05. So this could go all the way up to 105 if I'm considering a high volatility stock, or it can go down to 95, again, if I'm considering the same high volatility stock. And this matches our representation over here, where we have a stock price of time and time. We're more likely to deviate away from our expected mean returns drift if we have a higher volatility in comparison to a lower volatility. Now, in the same example that I did with mean returns, if I had a stock price of $1,000, then it can go up to 1,010 and 990. So instead of a plus $1 minus $1 difference, there will be a plus $10 and minus $10 difference. So what does this mean? Our volatility is a percent change in the same way mean returns is a percent change. Cool. So what does that mean for mean returns? Well, in the same way that we did for mean returns, we multiplied our mean return constant by our stock price. We're going to do the same thing with volatility. We're going to multiply our volatility constant by S. And keep in mind that this is going to be regarding our drift. And this is going to be regarding our shock. So if I were to put this back into the Brownian motion model, where my standard Brownian motion has standard deviation square root t and negative square root t. If I wanted to really represent a stock price, I would also multiply this by my volatility times my stock price. So depending on what this constant is, my 64% probability at every single point can either go up, meaning I'm less certain that my stock price is going to fall within a range at every moment in time, or it can go down. It can be scaled down. And this is for low volatility. So I can either have high volatility standard deviation looking like that, or I could have a low volatility standard deviation looking something like this. So now, for example, if I'm interested in this point right here, let's call it 2. If I have a low volatility, then I'm, without including the drift term, I'm expecting with a 64% probability that my stock price fall in this range. But if I have a high volatility stock in that same time increment at 2, I'm expecting my stock price to fall under this range. So this area is going to be high volatility, and this area is going to be low volatility. And keep in mind, all of this is a discussion on our shock. Cool. So now, if we were to add this back into the model, and here's going to be our financial asset model. We will have ds is equal to mu s dt plus our sigma, which represents our volatility, s dw. And again, this is going to be our drift, and this is going to be our shock. And this is going to be what we call geometric Brownian motion. And we will discuss the implications of this and really what it means in the next video.